Welcome back. In this video, you'll learn about Macaulay and modified convexity. Let's get to it. Alright, so the concepts of Macaulay and modified convexity, as you could probably guess, are related to the Macaulay and modified durations. Now remember that duration is a way to measure the sensitivity of the present value of a series of payments or cash flows to change based on the change in interest rates. In other words, duration reflects the rate at which the present value of a set of cash flows changes as interest rates change. Now, convexity, on the other hand, we want to know what is convexity. Convexity measures the curvature of the relationship between the present value of a set of cash flows and interest rates. It reflects the rate at which the duration of a set of cash flows changes as interest rates change. All right, so that's the general idea of what convexity is, and we'll look further into that as we go through this video. But as the topic of this video suggests, there are two different types of convexity that we can measure. We can measure Macaulay convexity, which we denote with capital M-A-C, capital C, or MacC, that stands for Macaulay convexity. And we also have modified convexity, which we denote with capital M-O-D, capital C, or ModC, which stands for modified convexity. All right, but now you might be interested in knowing how do we calculate the Macaulay convexity or the modified convexity for a set of cash flows. And that's what we're going to look at next, and we're going to start by looking at the Macaulay convexity for a set of cash flows. Okay, so the Macaulay convexity, or the MacC, is defined as the following. It's the weighted average of the squares of the times of the payments in a series where the weights are the same as in the Macaulay duration. All right, so if you remember, the Macaulay duration is also a weighted average, but it's just a weighted average amount of time until all payments in a series are made. The weight applied to each time is the present value of the payment made at that time divided by the present value of all the payments. And so just as a quick refresher, if we have the following timeline and these cash flows, we have a cash flow of C sub 1 at time equals 1, a second cash flow of C sub 2 at time equals 2, a third cash flow of C sub 3 at time equals 3, and so on, then the Macaulay duration, or the MacD, is calculated like this. It's equal to the time of that first payment multiplied by the amount of that first payment, and then we multiply it by the present value factor to the first power, because that will value that payment at t equals 0. And then we add that to the same calculation, but for the second cash flow, we have time 2 times the amount of the payment at time 2 times the present value factor squared, which brings that payment back to t equals 0. And then we do the same thing for the third cash flow, and so on. And then that's all divided by the present value of all of the cash flows. So it's the same calculation up here, but we're not multiplying each term by the time that the payments are being made at. All right, so this is how we calculated the Macaulay duration, and we could represent this calculation using sigma notation to have the more general form of the Macaulay duration, which looks like this. All right, so remember, the Macaulay duration, or the MacD, is just the weighted average amount of time until all payments in a series are made. And now comparing that to the definition of Macaulay convexity, the MacC is the weighted average of the squares of the times of the payments in a series, and the weights are going to be the same as in the MacD. And so what that means is that the only difference in the calculation between the Macaulay convexity and the Macaulay duration is that we're going to be squaring the time of each of the payments. All right, so here's what that looks like. I'm going to change this right here to be from the Macaulay duration to be the Macaulay convexity. All we have to do to make this calculation correct so that it calculates the Macaulay convexity instead of the Macaulay duration is just square each of these times in the numerator. So we'll have 1 squared, we'll have 2 squared, and we'll have 3 squared. And that would continue on forever if we had more payments or more cash flows after time equals 3. If we had a payment at time equals 4, then we would have plus 4 squared times c sub 4 times the present value factor to the power of 4. And then, of course, we would need to add the present value of that fourth payment in the denominator as well. All right, but this right here, this is the calculation for the Macaulay convexity of a set of cash flows. It's almost the exact same as the Macaulay duration. You just have to now square each of those times in the numerator. All right, and so using that knowledge, we can make a pretty easy adjustment to this generalized form for the Macaulay duration to make it the generalized form of the Macaulay convexity. All we have to do is square t in the numerator. By changing that t from just t to the first power to t squared, we now have the formula for the Macaulay convexity. It really is just that simple. It seems like it should be a whole lot more complicated than that, but that's really how you go about calculating the Macaulay convexity. The only difference between the MacC and the MacD is that in the MacC, we are squaring the time at which each payment is being made. Okay? So to summarize, the Macaulay convexity for a set of cash flows, MacC, is equal to the sum from time equals 1 to n of t squared times c sub t times the present value factor to the power of t divided by the sum from t equals 1 to n of c sub t times the present value factor to the power of t. You have the present value of all your cash flows in the denominator, and then you have the same calculation in the numerator, except you're multiplying each of those terms by the time at which the payments are made, and you're squaring that time. Okay, so this is how we calculate the Macaulay convexity, but now we want to look at how to calculate the modified convexity. All right, now in order to calculate the modified convexity, or the ModC, we first need to revisit the modified duration, just like we had to revisit the Macaulay duration to talk about how to calculate the Macaulay convexity. All right, so remember or recall that the modified duration is equal to the negative derivative of the present value function divided by the present value function, right? Remember that p of I is the present value as a function of I, the interest rate. It's a function that represents how the present value would change with respect to the interest rate. So if we had a set of cash flows like we have right here, this is the same timeline that we looked at for Macaulay duration and convexity. If this is a set of cash flows that we have, then the present value function, p of I, is equal to c sub 1 times the present value factor to the first power plus c sub 2 times the present value factor squared plus c sub 3 times the present value factor cubed, and then we can continue to add on from there. All right, now mathematically, we don't really like to write it like this though. The present value function, while it would be equal to each of these cash flows multiplied by their present value factors, it's better to write out what these present value factors would be in terms of I. So remember that v to the power of t is equal to 1 divided by 1 plus I to the power of t. And so you could also say that v to the power of t would be equal to 1 plus I to the power of negative t. Right? Moving a quantity with a positive exponent to the numerator makes that exponent negative. So we could rewrite the present value function like this. We'll have that p of I is equal to c sub 1 times 1 plus I to the power of negative 1 plus c sub 2 times 1 plus I to the power of negative 2 plus c sub 3 times 1 plus I to the power of negative 3, and we can continue on from there. All right, so this is usually what we're looking at when we talk about the present value function p of I. We have each cash flow multiplied by their present value factors, where those present value factors are expressed in terms of I explicitly. We have p of I is equal to a function in terms of I. Now in the calculation for the modified duration, we not only needed that present value function, we also needed the negative derivative of that present value function. And so if we took the derivative of this present value function, we'll have p prime of I, that is equal to the derivative of each of these terms. Now remember, because this function is in terms of I, we're going to be taking a derivative with respect to I, and so if you look at each of these terms, they all have a quantity of 1 plus I raised to a power. And so typically when you have a composite expression like that, or a composite function, and you're taking the derivative of it, you need to use the chain rule, right? For each of those quantities, we have an inside function of 1 plus I and an outside function of that quantity to a power. And so to take the derivative of that, you need to use the chain rule where you take the derivative of the outside function and multiply by the derivative of the inside function. But do note that the derivative of 1 is 0 and the derivative of I is 1. So when you're multiplying by the derivative of the inside function, we're just going to be multiplying by 1 for every single one of those terms. So we can kind of ignore the chain rule in this case. We can just multiply these exponents down via the power rule for derivatives and subtract 1 from those exponents as well. All right, so here's what we'll have. The derivative of our present value function will be negative c sub 1 times 1 plus I to the power of negative 2 minus 2 times c sub 2 times 1 plus I to the power of negative 3 minus 3 times c sub 3 times 1 plus I to the power of negative 4, and so on. All right, so this right here is the first derivative of our present value function. Now for the modified duration, we needed the negative version of that derivative. And so if we were looking to calculate the modified duration, you would then negate all of the terms of this derivative. All right, but we're not actually looking at the modified duration in this case. We're interested in the modified convexity. And so before we talk about how to calculate the modified convexity, I want you to remember something about duration. Remember that duration, such as the modified duration, measures the rate at which the present value of a set of cash flows changes as the interest rate I changes. The duration is essentially a rate of change, which is related to the idea of a derivative. Remember from Calculus 1 that you learned that the derivative represents a rate of change. And so it makes sense that the modified duration would involve the first derivative of the present value function in its calculation. And so in a similar manner, convexity is a rate of change describing how duration changes with respect to interest rates. It's the rate of change of the rate of change. And in calculus, we refer to the rate of change of the rate of change as the second derivative. And so it shouldn't be surprising that the calculation for the modified convexity is defined as follows. The modified convexity is equal to the second derivative of the present value function divided by the present value function. That right there is the definition of modified convexity. It's a very similar calculation to the modified duration, but instead of using the negative first derivative, we have the positive second derivative. All right, now if you wanted to figure out what this is equal to explicitly in terms of I, where you have all of the terms for the second derivative and the present value function, we could quickly find the second derivative of our present value function. We just have to take the derivative with respect to I of the first derivative. So let's do that real quick. Let's see what that second derivative would look like. P double prime of I is equal to the derivative of each of these terms. Now, once again, we would need to use the chain rule, but the derivative of the inside function for each of those terms is just 1, so we don't have to worry about that. We can just use the power rule for derivatives here. And so we'll have negative 2 times negative c sub 1, so we'll have positive 2 c sub 1 times 1 plus I to the power of negative 3. We subtract 1 from the exponent, and then we'll have negative 3 times negative 2 c sub 2. That will give us positive 6 times c sub 2 times 1 plus I to the power of negative 4. Remember to subtract 1 from that exponent again. And then finally, we'll have negative 4 times negative 3 c sub 3, which will be positive 12 c sub 3 times 1 plus I to the power of negative 5. And then we can continue on from there. All right, so that's what the second derivative of our present value function would look like. Of course, the terms will look a little bit different depending on the value of each of those cash flows, but this is how it would look in general. And so that would be in the numerator of the calculation for the modified convexity, and the present value function is still in the denominator. That would be this function right here. Okay, so this is the definition of the modified convexity. However, there is another way to calculate it. We can find another way to represent the modified convexity by analyzing the Macaulay duration and the Macaulay convexity. It's actually pretty cool, so let's take a look at that next. Okay, so here we have the calculations for the Macaulay duration for a set of cash flows and the Macaulay convexity for a set of cash flows. Remember that they're essentially the same calculation, except the Macaulay convexity has each of those times squared. All right, now what we're going to do here is actually add these two expressions together. We're going to take the MacD and add it to the MacC. And we can do that pretty easily because both the MacD and the MacC have a common denominator, right? They both just have a denominator, which is the present value of the cash flows. And so we can just add together the terms in the numerator and we have like terms, right? We can add the first two terms since they're both being multiplied by a present value factor to the first power. We can add the two second terms because they're both being multiplied by v squared, and we can add the third terms together because they're both being multiplied by v to the power of 3. And that would continue on forever, of course. We would add the fourth terms, the fifth terms, the sixth terms, and so on because they would be like terms since the powers of the present value factors would be the same. All right, so let's add everything together here. If we add 1 c sub 1 times v to 1 squared times c sub 1 times v, we will have 2 times c sub 1 times v to the first power, right? We have 1 c sub 1 and 1 c sub 1, which added together become 2 c sub 1, and they're still multiplied by v to the first power. Then for the next term, we'll have 2 times c sub 2 plus 2 squared times c sub 2. 2 squared is 4, so we have 4c sub 2 and 2c sub 2, which will become 6c sub 2, and then we have v squared. All right, and then we'll add that to the third terms added together. We have 3c sub 3 and 3 squared c sub 3. 3 squared is 9, so we have 9 plus 3, which is 12. So we'll have 12c sub 3 times v cubed, and we could add more terms from there. And then, of course, the denominator will remain the same because they do have a common denominator, and it's just the present value of the cash flows. And so I'll put that in right here. Okay, now at this point, we're almost at the really cool part where we can make a really cool connection to the modified convexity. But first, what I want to do is simplify this expression a little bit. Notice that every single one of these terms can be reduced by a factor of the present value factor to the first power, right? Every single one of these terms has at least v to the first power, so we can reduce each of those terms by a factor of the present value factor. So if we do that, this will be equal to 2 times c sub 1 plus 6 times c sub 2 times v, and then we'll have plus 12 c sub 3 v squared, and so on. All right, we just reduced each of those terms by a factor of v, so there's no v here. This v squared becomes v to the first power, and this v cubed becomes v squared. And then we'll do the same thing in the denominator. We'll have c sub 1 plus c sub 2 times v plus c sub 3 times v squared. And then we can continue on from there. All right, so this right here, this expression represents the value of the Macaulay duration plus the Macaulay convexity. And so here's where things get interesting. If you remember what we said earlier, the modified convexity is equal to the second derivative of the present value function divided by the present value function. Now, if we replace each of those functions with what they're equal to, and I'm taking this from the previous page where we calculated the second derivative and we wrote out the present value function itself, here's what the modified convexity will look like. We have the terms for the second derivative of the present value function in the numerator, and then we have the terms for the present value function in the denominator. Now remember that we could rewrite each of these quantities with a present value factor. I'm going to do that here so that we can more easily compare this expression to what we have up here. And so if I do that, this will become v cubed, this will become v to the fourth power, this will become v to the fifth power, then we'll have v to the first power, v squared, and v cubed. Here's what that will look like. And if I clean it up a little bit, this expression right here would represent the modified convexity. Okay, now in order to compare this expression to what we have up here, let's also reduce each of these terms by a factor of the present value factor, right? Notice that each of these terms can be divided by v to the first power. So let's do that. This will become v squared, so we'll have v squared. This will become v cubed, so we'll have v cubed. This will become v to the fourth power, so we'll have v to the fourth. This will become just c sub 1, and then we'll have v to the first power, and then v squared, so I'll write that in. And now, both of these expressions have the same denominator. Now if we compare the numerators, here's where things get pretty interesting. Notice that the Macaulay duration plus the Macaulay convexity has a numerator of 2c sub 1 plus 6c sub 2 times v plus 12 times c sub 3 times v squared, and so on. And if you look at the numerator of the modified convexity, we have 2c sub 1 times v squared plus 6c sub 2 v cubed plus 12c sub 3 times v to the power of 4. It's almost the exact same numerator that we have up here, except that each of these terms differ by a factor of v squared, right? 2c sub 1, 2c sub 1, 6c sub 2, 6c sub 2, 12c sub 3, and 12c sub 3. The only difference is that each of these terms is being multiplied by an extra v squared. If we multiplied v squared through the numerator here, all of these terms would match these terms right here. And so this is where the very cool connection occurs between the modified convexity and the Macaulay duration and Macaulay convexity. What we learn is that if we multiply the Macaulay duration plus the Macaulay convexity times v squared, we will have the modified convexity. So what we can say here is that the modified convexity is equal to the Macaulay duration plus the Macaulay convexity times v squared. Or another way that you could write it is that the modified convexity is equal to the Macaulay duration plus the Macaulay convexity divided by 1 plus I squared. All right, these would be equivalent ways of representing that same expression. But the bottom line here is that the modified convexity can also be calculated in this way. If you can find the Macaulay duration and the Macaulay convexity, and then add those two values together and multiply by v squared, you will have the modified convexity. It could be a nice little shortcut to quickly calculate the modified convexity without needing to write out the present value function and taking the first and second derivatives of that function. All right, it's kind of a cool calculation because it connects the modified convexity to the Macaulay duration and the Macaulay convexity, similar to how the modified duration was equal to the Macaulay duration times the present value factor to the first power. And so it's just kind of a neat result that shows how these different measurements are related. Okay, but to summarize, the modified convexity for a set of cash flows can be calculated in two different ways. The ModC can be found by taking the second derivative of the present value function evaluated at I divided by the present value function evaluated at I, or you could find the Macaulay duration and the Macaulay convexity, add them together, and multiply by v squared, and that will also give you the ModC, or the modified convexity. Okay, and so with that, that is all you need to know about Macaulay and modified convexity. In this video, we were just looking at how to simply calculate them and where their formulas come from. Being able to calculate these different types of convexity will become important in a later lesson. But for now, if you want to get some practice, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.